Welcome, calculus folks. Last lesson of this short unit on curve sketching, and nothing new really. This is the putting it all together day, really. Um, I've only got two examples for you. One of them I'm at this warm up. Hopefully you've got it tried and you got all your work in front of you and all that other business. Um, and I'm going to go through this one fairly fairly slowly in depth, making sure that you can do this. And then I'm going to go through the example from the note pretty quickly. I'm going to actually just have all the work done and talk about it. And hopefully you've got a copy of that in front of you as well, the second example, because it's really, really long. Um, the book has several examples for you to sort of go over and make sure that you're doing all these things. Um, I also want to mention the CEMC courseware, which hopefully I've got a link to on the calendar. That it has several examples as well, all different than the ones that I've got, the ones that I've done. So if you need more examples, go find them. Okay, there's lots of stuff to be done. Um, Again, this is a putting it all together day. So draw an accurate sketch, including all work of this function. So right now, we kind of are thinking of our algorithm as being, at this point anyway, aim, asymptotes, intercepts, and min maxes, right? Min maxes. But we'll actually make that a little more complex because we had all that first derivative test, second derivative test, concavity, all that other business. So um, we are actually going to go beyond this today, and I'm actually going to go through. So, what would you do first? Well, it's almost like we have several things that we can kind of work on. So, what I'm going to do, and you kind of see the Desmos sketch peeking out down there. That's what we're going to build. I'm going to put it down there. Just get it out of the way for now because we need lots of space. In fact, I'm going to delete this thing too, just because we need lots of space. What would be the first thing? Well, probably even to get our functions sketch, would we want to find the intercepts, right? So let's find the intercepts. We've got no asymptote, so let's find the intercepts. There's kind of a couple of things that are going to be going on here. I'm going to have a little T chart that's going to be all of our important points running, and then I'm going to have a sign chart here, and then I'm going to have a sketch here. And these are all sort of things that we are building. All right, things that we are building. There's X and there's Y. So the intercepts, I know when X is 0, I put in X is 0, Y is 0. I don't even need to show that calculation. Notice that that's one of our X intercepts as well, but we're going to see that there's going to be more, right? So set Y equals 0, and we can find the intercepts. All right, so one of them is that common factor there. Whoops. And then now, how do we deal with this? Well, this is a cubic, right? That doesn't factor nicely, so I'm going to have to use the factor theorem. All right, so I look and find something that makes that 0, and f at 1 equals 0, so therefore x minus 1 is a factor. And so I'm going to factor that. I've common factored out the x. I don't have to worry about that. I'm factoring the thing that's in the brackets. Watch your placeholder there. That'll goof you up if you haven't done any factor theoreming for a while. Can you use synthetic division if you've taught yourself synthetic division? Absolutely. Remember, the whole process is finding stuff that when I subtract, it will disappear. Subtract there, and then this comes down, plus x, need more space, x squared minus x, subtract, and And this one's supposed to go evenly, right? And if it didn't, I goofed something up. It was, when didn't it go evenly? Remember when we were finding equations of oblique asymptotes, it never went evenly. So therefore, then notice that this actually factors as well. This is x minus, or x plus 2, x minus 1. And so then I can go, I'm going to go back to my other color. This was like a the sidebar. Then y is x times x minus 1. Notice there's another factor of x minus 1 over here. So this is x minus 1 squared times x plus 2. And then I see the x-intercepts are x equals 1, 0, and minus 2. So those all go on 1, minus 2 is an x-intercept, and 0 is a y-intercept. And so notice that those can go on my chart, my sign chart, right away. And up here somewhere, because I want y prime, and y double prime. That's where this is 0, 0, and 0. And I know from functions, right? Actually, I can do a pretty good sketch of this almost straight off now. There's 0, 1. I'm going to spread it out just a little bit here. There's a bounce there, right? Bounce. Remember the good old bounce. And then there's minus 2. The sketch, degree 4, starts high, ends high. Starts high, ends high, and I can do a pretty good sketch of this right away, knowing that there's a bounce there. So starts high, ends high, goes something like this. I'm going to wait just a little bit to do this because I'm going to have some details added, but just, just faintly, just so we can get an idea. And it's going to bounce like this. I'll maybe come back and delete this later so I can add some more detail. But that's the MHF4U sketch, right? Where we'd want to do, maybe we'd calculate a point in here so we could get some scale, but that's MHF4U. What's next? So next, notice then we could put in our sign chart, I suppose. It's minus there, positive here, bounce and stays positive. Good, and this one doesn't help us very much, but now I'm going to get into the first derivative, right? First derivative of a polynomial function, since y is equal to x to the exponent 4 minus 3x squared plus 2x, y prime is 4x cubed. This is kind of, if you're working with a neighbor, somebody could do the first derivative and somebody could do the second derivative in the analysis, right? The first derivative analysis is things like mins and maxes. Second derivative analysis is things like points of inflection and concavity. Right, great. So then I'm going to set y prime equals 0. And what do I got? Guess what? It's another cubic. Right, so this is another factor theorem. I'm going to divide everything by 2 to simplify it first. Remember that now I'm solving the equation. This is the second derivative, or this is the first derivative. But when I'm solving the equation, I can divide everything by 2. All right, so g at 1 equals 0, therefore x minus 1 is a factor. Yeah, long division again. Need another placeholder. Multiply by 2 so that when I subtract it, it'll disappear. Subtract, I get 2x squared, write down 3x plus 2x. Are you keeping up? Are you staying awake? Yes, that's the question. Well, you've got all this done in front of you. You're just checking, right? You're not copying. Um, so notice this doesn't factor. But if I use my quad solver or quadratic equation, 0.366 about, and negative 1.366. And so those go back up here. I'll add 0.366 to this and negative 1.366. See, this will be later. I'll actually pound a bunch of values into my calculator and get the output values. But also I can add these to my sign chart. Remember, it was also 0 here, right? 0 here. And at negative 1.366 was 0 there. And that gives us our intervals of increase and decrease. I shouldn't analyze it, but what do I mean by analyze? Remember this original function, that one right there, that original function, I took out this factor, right? So y prime is equal to 4x cubed minus 6x squared, or 6x plus 2, which is also the same as this function. And then I could do the analysis on that to find out where it's positive or negative. But I can also see from my advanced function sketch, it decreases until here, right? This is my negative 1.366. And then it increases to here, this is my 0.366, because there's a maximum. Right? So it's going to be negative along there, negative to there, increases from here to here, then decreases, and then increases. And I can see all my minimums and maximums straight from there. But I could also use the second derivative, right? So the second derivative test is coming up. So my second derivative, 12x squared minus 6, set, what are we looking for when we set the second derivative equal to 0? Right, for points of inflection. So then we have 0 equals 12x squared minus 6. Divide both sides by 12. Tidy up, square root. And that gives me some more values to add to my graph and my sketch. 1 over the square root of 2 and negative 1 over the square root of 2. Those values are, well, you pound them into your calculator, but I can see where there's the negative one's going to be right about there, right? This is negative 1 over the square root of 2. Positive 1's going to be right over there, because there's the frown. Right? I'll color that in. There's the frown. The rest are all smiles. So that point right there is 1 over the square root of 2. Negative 1 over the square root of 2. And in here, 1 over the square root of 2. That's 0 there. 0 there. Smiling out this way. Frowning in the middle. And notice right there, there's the second derivative test for a minimum. I have the first derivative is 0, and the second derivative is positive, so I know it's a minimum. Similarly here, first derivative is 0, second derivative is negative, so I know it's a maximum, and so on. And there's our graph. Notice that we go back on our calculator, or Desmos works good too, and get all these values and substitute them in. All right, phew, what a lot of work. What a lot of work, but talk about everything that is important in calculus all on one question. Look at that. And we've got another one coming up in part 2. That's a rational function, and we'll talk about kind of our algorithm for sketching graphs in just a moment.